All right, hello everyone, and welcome to my channel. We do educational videos on this channel. We try to go into theories of everything with deep dives and try to illustrate how they can be used, how you can use them in your own life to shift your paradigm, help you awaken to 5D consciousness, organize your holistic worldview, and so on. And so today is our 492nd video that we've done on the reciprocal system of theory from Mr. Dewey Larson. And Mr. Larson was an American engineer who lived in the 20th century. He was born in 1898 and died in 1990. He had his first epiphanies about the reciprocal system back around 1930 when he was working as an engineer out west in Portland area, and worked on it, kept his day job, worked on it at night, trying to develop his ideas. At first, he was working on a much smaller project, but then he began to see the universality of some of the conclusions that he had come to, and worked it out. In 1959, he proposed his two fundamental postulates about how he believed the universe operated. And that's just two sentences. And he was one of the first, or one of the few, not the first, but one of the few scientists who, proposed a universe that was constructed upon motion, not matter or energy, but motion. And his first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So that's why they call it the reciprocal system. The universe is made out of motion, and motion is the relationship between space and time, which automatically sets up a reciprocal relationship between space and time. Space and time are not entities in and of themselves. They only exist together in motion. And space and time are identical with one another, except that they are reciprocals in motion. They have the same qualities, just like all reciprocals do. And they come in 3 dimensions. Space, time, and motion come in 3 dimensions. They come in discrete units. Now, when Larson is referring to motion, he's referring specifically to more generalized kind of motion called scalar motion. The scalar motion is a motion that has a magnitude, but it has no specific direction, which you can model using a balloon that you put dots on. As you blow up the balloon, all the dots will be moving away from each other. And that is a motion that does not have a specific direction. It has, in fact, it's moving in all directions. Every dot is moving away from every other dot. And if you contract the balloon, then every dot will be moving toward every other dot. And Larson analogizes those 2 movements. The outward motion he calls the progression, the inward motion gravitation. And then basically manifestation is the kind of the process of going from that outward motion of the balloon to an inward motion of the balloon. And then Larson's second postulate states that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, I think we can kind of debate about the details of that, kind of mathematical, geometrical, logical statement, but the main point, I think, is that he's using the rules accepted by the majority of scientists in order to take his first postulate and put it through a process of deduction, kind of an if this, then that approach. And so he uses the principles of mathematics, like especially probability principles, and the principles of geometry in order to move from his first postulate. Okay, if my universe is made out of motion, and motion is the relationship between space and time, and they both have three dimensions, they all have three dimensions and come in only discrete units. And then I have these laws of math and geometry and so on. What does that, mean, in the long run when I put it through this if this then that approach? So from that then Larson derived his theoretical universe, what my universe would look like if my postulates were correct. And then in subsequent publications, including the one that we're looking at today, he compares his theoretical universe with the measured universe of the legacy scientists, all the army of mainstream scientists out there who work in laboratories and make measurements, do tests, make measurements, and compile them in scientific tables about things like, in this book, for example, this book is called The Basic Properties of Matter. And so this is about chemistry, and Larson comes up with equations to describe many of the basic properties of matter, such as the melting point and the compressibility and the specific heat. And then he applies his equations to all of the elements and many compounds and compares them with the scientific tables. So Larson basically arrived at a theoretical universe, and then he compares his theoretical universe with the observations of the legacy scientists and see if he, actually just through theory is able to arrive at the same results that a scientist or an army of scientists can arrive at with, billion-dollar grants, billion-dollar facilities, thousands of scientists working around the clock for decades, if not centuries, in order to arrive at these results. Or maybe it would be more efficient if it was just one guy with a theory, and he can come up with the same results as the sum total of the scientists over the last 3,000 years or whatever. And it's pretty interesting that he's able to reproduce these results almost entirely, and in some cases even improve on them. So today we are looking at chapter 14 of this book, Basic Properties of Matter. This book was written in 1987, just 3 years before he died. And it is volume 2 of his 3-volume work of the second edition of The Structure of the Physical Universe. So the first volume is called Nothing But Motion, which is mainly on atomic physics with a little bit of organic chemistry. And then this is mainly about chemistry, basic properties of matter. And then he's got a third volume, which actually he wrote second, which is called Universe of Motion, which is on astronomy. But he also has books on, astrophysics And he has 2 books on economics. He's got a book on metaphysics that covers subjects like philosophy, religion, psychology, biology, and he also, some of his followers have written on other subjects such as meteorology and geology, crypto history, crypto archaeology. So the reciprocal system, the main point is that it is a generalized system. So once you understand how the system works, you can plug it into whatever subject you like. It's a generalized theory. So Larson, even though this chemistry stuff is maybe in the weeds for you, maybe you don't understand the chemistry stuff. What you're trying to do is get the concepts out of it, because he uses the same concepts when he approaches economics or astronomy as he uses when he approaches chemistry. It's a method. Once you learn the method, then you can apply it to whatever subject you want. So we're looking here at Larson's actual words in order to kind of understand what his process is, so that we can kind of emulate that once we realize how to work the system. And so that was just an abbreviated explanation. But if you go to any of my first 474 videos on this subject, you can get a little bit more detail about how the fundamental postulates, what are the ramifications of the fundamental postulates, and kind of how he derived his deductive theoretical universe. Okay, we're going to take over here toward the end of chapter 14 on the basic forces. So here he's kind of looking at gravitation, electricity, and magnetism. These are not fundamental forces. They are motions, just like everything else in Larson's universe. Everything is a kind of motion, a relation between motions, or something like that. And so he's talking about gravitation, electricity, and magnetism, and how they fit into his overall structure. Okay, clarification of the gravitational force equation is not only important in itself, but has a further significance in that it opens the door to an understanding of the general nature of all of the primary force equations. Each of these equations is an expression representing the magnitude of the force, or the apparent force, that is exerted by one originating entity, the mass or the charge, on another of the same or equivalent kind at a specified distance. All take the same general form as the gravitational equation. Basically, force equals a constant times mass 1 times mass 2 over the distance squared. With the benefit of the information developed in the earlier pages of this chapter, we may now generalize the equation by replacing replacing m with x, replacing mass with x, which will stand for any distributed scalar motion with the dimensions t over s to the n power. Now, in Larson's system, the universe is made out of space and time. The universe is made out of motion. Motion is the relationship between space and time, and they are quantized. Space, time, and motion come only in discrete units. They don't come in fraction or decimals. You have to have full units. And what that means is really all of our fundamental scientific quantities are relationships between space and time. So, for example, speed is space over time. The car is moving 12 miles per hour. 12 miles of space in 1 hour of time. Space over time is speed. But every other kind of scientific entity scientific quantity is also a relationship between space and time. For example, matter in Larson's system is time to the third power over space to the third power. Energy is simply time over space. Acceleration is space over time to the second power. Pressure is time over space to the fourth power, and so on and so forth. So that's kind of what he's saying here. Any distributed scalar motion with the dimensions t over s to the n, and introducing a term y with the value of 1 over s times the quantity s over t to the n minus 1. So instead of using his force equals km m prime over d squared, he's now using the primary force equation is that F equals k constant x times y times the quantity x prime over d squared. I'm not sure that I followed that completely. The x is t over s to the n. So that's t over s, or t squared over s squared, or t to the third over s to the third. So those are, 1, 2, and 3-dimensional energy. The 3-dimensional energy is mass. The 2nd-dimensional energy is momentum. But then he's got the y term is a value of 1 over s times s over t, the quantity s over t, to the n minus 1. So we go down a power for this, and we multiply in s over t instead of s over t is the dimensions of speed. And so you would have space over time, but space to the second over time to the second would be 2-dimensional speed. And then s to the third over t to the third would be 3-dimensional speed. Because remember that motion, space, time, and motion all come in 3 dimensions. But really, 3 dimensions of space only occupies 1 dimension of motion. And so there are at least 1, if not 2, more dimensions of motion that don't fit into the, reference system. Okay, let's move on. I'm still a little bit confused about that equation, but that's kind of the nature of the reciprocal system, is that you kind of have to be okay with being confused. A lot of times, Larson will answer your question eventually if you keep reading, but sometimes you might have to let it marinate around in your mind for a while before you are able to get a clue of what he's talking about in every instance. Again, we're talking about one guy with no budget doing this, so you can't expect it to be on a silver platter for you. Since only one dimension of an n-dimensional scalar motion is effective in the space of the conventional reference system, the effective space-time dimensions of the motion participating in the force equation are t over s. By definition, force has the dimensions of t over s squared. The function of the term y in the primary force equation is to reduce t over s to the n to t over s, and to introduce the term 1 over s that is necessary to convert t over s to t over s squared, to convert energy to force. In the case of the gravitational equation, this involves multiplying by s to the second power over t to the second power times 1 over s equals space over time to the second power, which is acceleration. These are the dimensions of acceleration. In the Coulomb equation, the correction factor y is merely 1 over s. The term x prime over d squared is a combination of two ratios and has unit value in the unit statement of the equation. The numerical constant k is also unity if all quantities are expressed in units that are consistent with the units in which the space and time magnitudes entering into the equation are measured. Where one or more of these quantities are expressed in units of another kind, the difference in the size of the units appears as the value of the numerical constant k. In the gravitational case, for example, the gravitational constant reflects the result of expressing mass in terms of a special unit, grams in the CGS system, rather than in seconds to the third power over centimeters to the third power. In essence, all that the force equations do is to reduce the scalar motions, mass, charge, etc., to their effective one-dimensional values, introduce the 1 over s term that relates the motion to the corresponding force, and correct for any inconsistencies in the units that are employed. It is somewhat of an anticlimax to arrive at such a simple explanation after years of exploring much more complicated hypotheses, but the simplicity of this result is consistent with the general nature of the findings in the basic areas of other physical fields. There are many complex phenomena in nature, to be sure, but throughout the development of the details of the universe of motion, we have found that the fundamental relations are quite simple. As noted earlier, the reference point of a scalar motion, the point in the fixed reference system to which an object in the scalar motion system is coupled, may be in motion vectorially. The mass of this object is a measure of its three-dimensional distributed scalar motion, the inward gravitational motion. The vectorial motion is outward, and in order for it to take place, a portion of the inward gravitational motion must be overcome. The mass is thus also a measure of the magnitude of the resistance to vectorial motion, the inertia of the object in the light of the points brought out in the preceding pages. It is evident that in these manifestations of mass, we are looking at two aspects of the same thing, just as in the case of the rocket, where the quantity of acceleration imparted by the combination products, or the force, is the same as the quantity of acceleration imparted to the rocket. This point was not recognized by the early investigators because they were not aware of the existence of motion in different scalar dimensions. It appeared to them that two different quantities were involved, a gravitational mass and an inertial mass. Very accurate measurements showed that these two masses are identical, a finding that the physics of that day could not explain. As one observer says, within the framework of classical physics, there is no explanation, end quote. When, the quote continues, actually, when attention was directed to the problem, it seemed like a complete mystery, end quote. A step toward solution of this problem was taken by Einstein. In the absence of an understanding of scalar motion, he was not able to see that gravitation is a motion, but he formulated a principle of equivalence in which he postulated that gravitation is equivalent to a motion, since he viewed motion as synonymous with vectorial motion. The postulate meant that gravitation is equivalent to an accelerated frame of reference, and it is often expressed in these terms. but such an equivalence is inconsistent with Euclidean geometry, as explained by Tor Gerholm. Quote, if acceleration and gravitation are equivalent, we must apparently also be able to imagine an acceleration field, a field formed by material forces. It is easy to realize that no matter how we try, we will never be able to get such a field to have the same shape as the gravitational field around the Earth and other celestial bodies. If we want to save the equivalence principle, if we want to retain the identity between gravitational and inertial mass, then we are forced to give up Euclidean geometry. Only by accepting a non-Euclidean metric will we be able to achieve a complete equivalence between the inertial field and the gravitational fields. This is the price we must pay. End quote. Identification of gravitation as a distributed scalar motion has now thrown an entirely new light on the situation. Gravitation is an accelerated motion, but it is not geometrically equivalent to an accelerated frame of reference. Einstein's attempt to reconcile these two phenomena by resort to non-Euclidean geometry is misdirected. Whatever mathematical results are obtained by the use of this expedient, actually not very many, as Paul Davies points out, quote, technical problems of a mathematical nature render all but the simplest systems hopelessly insoluble, end quote. So by the use of this expedient are not indicative, the results obtained by use of this expedient are not indicative of the true relations. The scalar gravitational motion of an object and any vectorial motion that it may possess are quite different in their nature and their properties. In the case of the propagation of radiation, the principal stumbling block for the ether theory, was the contradictory nature of the properties that the hypothetical substance ether must possess in order to perform the functions that were assigned to it. Einstein's solution was to replace the ether with another entity that was assumed to have no properties, other than an ability to transmit the radiation, an ability which he says we should, quote, take for granted. Similarly, the obstacles to accounting for the observed results of the addition of velocities were the existence of absolute magnitudes and fixed spatial coordinate locations. Here, the answer was to deny the reality of absolute magnitudes, and, as Einstein says, to, quote, free oneself from the idea that coordinates must have an immediate metrical meaning, end quote. Now we find that that he deals with the gravitational problem in the same way, loosening the mathematical constraints rather than looking for a conceptual error. He invents the, quote, equivalent of motion, a hypothetical something which has enough of the properties of motion to enable accounting for the mathematical results of gravitation, at least in principle, without having those properties of vectorial motion that are impossible to reconcile with the observed behavior of gravitating objects. In all of these cases, the development of the theory of the universe of motion has shown that the real reason for the existence of these problems was the lack of some essential information. In the case of the composition of velocities, the missing item was an understanding of motion in time. In the other two cases cited, the problems were consequences of the lack of recognition of the existence of scalar motion. All right, that is the end of the chapter. Now, to complicate things further, I have to... I didn't really understand exactly what he was talking about with that equation there, and I'll have to look at that again. for the umpteenth time. But I have to disagree with Larson on a number of things here, and I believe that some of Larson's associates also disagree with him, especially the late Dr. Bruce Perrett. In Dr. Perrett has something that he calls RS2, the re-evaluation of the reciprocal system, where he takes Larson to task on a few items, especially Euclidean geometry. And to me, the Euclidean geometry that Larson is clinging to here and that he uses in his second postulate does not explain scalar motion as the second and third dimensions of scalar motion, at least. And Dr. Perrett proposes using projective geometry, which also includes Euclidean geometry. And so Perrett uses this cascade from projective geometry to affine geometry to metric geometry and then to Euclidean geometry as a subset of projective geometry. And I have to agree with him on that. I still haven't quite figured out the steps that Larson is taking here, but I also know that Dr. Perrett took Larson to task on many of his aspects of electrical and particularly electrical phenomena. And so I think that we have gone through a lot of Dr. Perrett's work, but we're going to go through it in more detail here in the future. And I think we're going to do it with an attempt to pinpoint what Larson is kind of getting wrong according to Perrett in this chapter and a few of the chapters in this area of this book that have to do with the electricity, especially, and the magnetism. So tomorrow we're going to be starting chapter 15, which is on electrical storage. So this is another kind of contentious chapter. I must say that the electricity stuff is, among all of Larson's writings, it's the stuff that I understand the least. And so it's the stuff that I'm most suspicious of not being correct. And Larson did admit that he was subject to error. He would say that the theory itself is correct. Whether I succeeded in applying the theory correctly is a different matter. Okay, so thanks for tuning in today.